Here's a pretty good problem from high school calculus. It's a fairly simple problem and tests your understanding of increasing and decreasing functions and how they relate to the first derivative. Let's try to solve it. So the problem wants us to determine whether f of x is an increasing function, decreasing function, or whether it has a local maximum or minimum. So basically we need to determine whether f dash x is greater than 0, less than 0, or equal to 0 in the required interval 0, root 2. Let's begin by computing f dash x. First differentiate g of x and we just write g dash x, and the second term is g of 4 minus x and the derivative of that is g dash of 4 minus x. Now using the chain rule we differentiate 4 minus x, so we get a negative sign. Alright, now let's take a minute to revisit the definition of an increasing function, and that will tell us exactly what to do next. The first point basically gives us the definition of a strictly increasing function. A function is said to be strictly increasing if x1 less than x2 implies phi of x1 less than phi of x2. The important thing to notice here is that the signs of inequality are matched on both sides of the implication. So the very same relationship can also be written as x1 greater than x2 implies phi of x1 greater than phi of x2. Of course, in case of a decreasing function, the signs of inequality would have been flipped. The second point recalls a fact from basic calculus, which is that if the first derivative of a function is positive in a certain interval, then in that interval a function is strictly increasing. Let's go back to the problem and see how we can use this fact. The problem does not give us any information about the sign of g dash x. However, it does tell us that g double dash x is greater than 0. This tells us that g dash x is a strictly increasing function. We can therefore apply the definition of an increasing function that we just recalled to g dash x. That is to say, if x is less than 4 minus x, then g dash of x is less than g dash of 4 minus x. We can now simplify the left-hand side of the implication to see that the condition x is less than 4 minus x is the same as the condition x is less than 2. This allows us to say that x is less than 2 implies g dash of x minus g dash of 4 minus x is less than 0. But as we see above, this term is the same as f dash x. We can therefore say that x less than 2 implies f dash x is less than 0. We can now go back to the question and observe that the domain of the function g is the closed interval 0, 4. Therefore, that is also the domain of the function f. Well, we can now finally make the following statement. In the open interval 0, 2, f is strictly decreasing. Well, that's that. We are ready to select the correct answer. We only need to observe that the open interval 0, root 2 is a subset of the open interval 0, 2. Okay, problem solved. We can now say that in the open interval 0, root 2, f is a decreasing function. Option B. Let's try to solve some similar problems to make sure that we understand the concepts involved in this problem deeply enough. In our original problem, we were concerned with the interval 0, root 2. And we saw that the answer to that problem was option B, f is a decreasing function. Let's see what happens if we change the interval from 0, root 2 to the open interval 3, 4. Can you now solve this new problem? To solve this new problem, we actually use the exact same logic as before. Again, we say that since g double dash x is greater than 0, therefore g dash x is an increasing function. But this time around, instead of considering x1 less than x2, we consider x1 greater than x2. That is to say, x greater than 4 minus x implies g dash x is greater than g dash 4 minus x. After this, we can proceed as before. But this time around, we arrive at the conclusion that in the interval 2, 4, f is strictly increasing. So there we have our answer. If we were considering the open interval 3, 4, then the correct answer would be option A. F is an increasing function. Alright, Let's try one last variation to the problem. What if instead of the open interval 0, root 2, we were concerned with the open interval 1, 3? Well, this should be pretty straightforward. We've already seen that in the interval 0, 4, the function decreases in the interval 0, 2 and then increases in the interval 2, 4. I think we can guess what happens at the point x equal to 2. To confirm our suspicion, let's find the value of f dash of 2. We know that f dash x is equal to g dash x minus g dash 4 minus x. Therefore, f dash 2 is g dash 2 minus g dash 2 is equal to 0, of course. So we now know that x equal to 2 is a critical point of the function. The only thing remaining is to find out whether it's a local minimum or a local maximum. If you recall what is called the first derivative test for maxima or minima, it says that if a function has a negative derivative to the left of a critical point and a positive derivative to the right of a critical point, then that critical point is a point of local minimum. Well, in our case, we know that the function decreases in the interval 0, 2 and increases in the interval 2, 4. Therefore, it follows that in the interval 1, 3, f has a point of local minimum. Option D.